think, the bedrock of reality.
To say the least.
Right, we were examining a stack of highly theoretical physics papers published in early 2026. These are authored by independent researcher Michael R. Bermia Jr.
And we're looking at a few different texts here, right?
Yes. This includes his Gravity Research Foundation essay, which is titled Replacing QFT, as well as the really extensive multi-volume set of the time force hypothesis Principia.
The Principia.
Yeah, these documents lay out the mathematical and conceptual architecture for an entirely new paradigm. And when I say new paradigm, I mean a ground-up reconstruction of how the cosmos operates.
So the mission today for you, the listener, is to evaluate the absolute feasibility of this time force hypothesis, which we will be referring to as TFH, just to save time.
TFH, exactly.
This is a radical proposal. It attempts to completely replace both general relativity and quantum field theory. So we aren't just going to explain what this hypothesis is. We're going to rigorously explore if it actually works.
Can it actually hold up to the math?
Right. Can a single, damped, four-dimensional scalar wave really explain gravity, quantum mechanics, dark matter, and the arrow of time all at once?
It's a huge ask.
Okay, let's unpack this. Because usually in physics, we have one set of rules for the incredibly large general relativity and a completely different set of rules for the incredibly small quantum field theory.
And they don't get along.
No. As anyone who follows physics knows, they notoriously refuse to play nicely together.
That incompatibility is really the great shadow hanging over modern physics. I mean, for nearly a century, we've had these two incredibly successful frameworks. General relativity gives us the macro universe.
The big stuff.
Right. It tells us that gravity isn't a pulling force, but rather the curving of a four-dimensional fabric called spacetime. Massive objects like stars and planets, they warp this fabric, and that warping dictates how things move.
It's smooth, it's continuous and geometric.
Exactly. On the other hand, we have quantum field theory, or QFT, which rules the micro-universe. It describes a jittery, highly probabilistic world made of discrete particles and fields.
Governed by the fundamental forces.
Governed by three fundamental forces, the electromagnetic force and the strong and weak nuclear forces. And it is not smooth at all. It is quantized, chunky, and inherently uncertain.
Right, and when you try to smash the math of the smooth, curving fabric, together with the math of the chunky, jittery particles, like, say, when you try to understand the center of a black hole.
Or the exact moment of the Big Bang.
Yes, the equations just completely break down, they spit out infinities, they just stop making sense. It's like trying to play a symphony using the rules of baseball.
What's fascinating here is that TFH doesn't just try to tweak the existing math to force those two standard models together.
Because people have tried that for decades.
No, absolutely. We've seen decades of attempts, most notably with string theory or loop quantum gravity, but those often just add more complex mathematical layers, like extra hidden dimensions to patch the holes.
It's just adding more duct tape to the problem.
Basically. Bermia's proposal does something entirely different. It demands a complete ontological inversion of how we view the universe.
An ontological inversion. Okay, so flipping our understanding of what actually exists completely on its head.
Exactly that. In standard physics, we assume space and time are the fundamental stage.
Right.
And matter and energy are the actors moving around on that stage.
Okay.
TFH throws out the stage entirely. It composes an energy-only ontology.
Energy only.
Yes. It argues that there is no fundamental space-time fabric waiting to be bent, there are no separate little billiard ball particles, and there are no independent forces acting at a distance.
So what is there?
It proposes that there is only a single real scalar field, which the author labels with the Greek letter phi. And this field is propagating through a four-dimensional Euclidean bulk.
Hold on, let's stop right there. Four-dimensional Euclidean bulk is a hefty piece of jargon. Let's unpack that for a second. When I hear Euclidean, I think back to high school geometry.
Right, flat planes.
Flat planes, straight lines, angles adding up perfectly to 180 degrees.
That high school geometry instinct is spot on. Euclidean space means flat space. It is entirely uncurved. In Einstein's general relativity, space is non-Euclidean. It warps and bends in response to mass.
Like the classic bowling ball sitting on a trampoline analogy.
Yes. But in TFH, the fundamental backdrop, the bulk, as physicists call the total volume of space, is perfectly flat, rigid, and four-dimensional. It doesn't bend, it doesn't warp, it just sits there. The stage is completely inert.
So if the stage isn't bending to create gravity, and there aren't any actual particles bumping into each other, what is actually happening in this model?
The only thing happening is the movement of that single scalar field, phi. A scalar field is really just a mathematical way of saying that every point in that flat 4D space has a specific value or magnitude of energy assigned to it.
Okay.
According to TFH, all the complexity of our universe, space, time, particles, forces, the geometry we perceive, is entirely an emergent property of how that single field moves, structures itself, and loses energy over time.
Okay, to make this visceral for you, the listener, the author uses a brilliant analogy that I really want to lean into because it grounds this massive concept beautifully.
The weather analogy.
Yes, the analogy of the meteorological front. Think of a weather front right here on Earth. The Earth's atmosphere is a massive, three-dimensional ocean of air. It's everywhere.
Right.
But a weather front, say a cold front, where a freezing air mass violently slams into a warm air mass, is this highly active dynamic boundary. It's a localized zone of intense energy, storms, and pressure changes moving through that atmospheric ocean.
Exactly.
Now scale that up dimensionally. Imagine a vast, infinitely flat, four-dimensional ocean of pure energy. According to the time force hypothesis, our entire observable universe, every star, every planet, your body, the phone in your pocket, the air you are breathing, all of it is just the moving three-dimensional boundary of this field.
It is the wavefront of this 4D energy ocean as it advances.
We are quite literally living on the crest of a cosmic wave.
The weather front analogy gets to the very heart of the hypothesis. The bulk of the atmosphere might be relatively quiet, but the front is where the action is. In TFH, the four-dimensional bulk is essentially empty or uniform.
But that boundary,
But that boundary, that advancing wavefront, is where the scalar field becomes highly structured, turbulent, and complex. All the energy of the universe is concentrated and trapped in this narrow, moving band.
wow.
But to really grasp the feasibility of this, to understand if this could actually be how reality works, we have to look at how TFH redefines arguably the most mysterious concept in all of science.
Which is time.
Time. This is the most crucial intervention the theory makes because it addresses what Bermea calls the crisis of time.
The crisis of time. This is something that doesn't get talked about enough outside of theoretical physics circles, I think. We all just assume time is time. Your watch ticks, you get older, the day ends.
Right, it feels obvious.
But in physics, time is an absolute mess right now, isn't it?
It is a profound contradiction. Let's trace it back. In Newtonian mechanics, time is simple. It is a universal, absolute clock ticking away uniformly in the background of the universe.
Doesn't care what you are doing.
Exactly, or how fast you are moving. A second is a second for everyone, everywhere.
But then Einstein comes along in the early 20th century and completely ruins that simple picture.
He revolutionized it. General relativity turned time into a physical dimension, woven together with the three dimensions of space into a four-dimensional fabric spacetime. In this model, which is often called the block universe, past, present, and future effectively coexist as coordinates in a massive block. More importantly, time becomes malleable.
Because if you travel near the speed of light or if you stand near a supermassive black hole, your experience of time actually slows down relative to someone back on Earth.
Yes. Time is no longer an absolute background clock. It is a dynamic physical participant in the universe.
All right, and that works perfectly for stars and black holes. But then you jump over quantum field theory to look at atoms and subatomic particles, and suddenly time reverts back to being a rigid external parameter.
It does.
In QFT, time isn't a bendable dimension. It's just a fixed ticker tape running in the background, governing the evolution of quantum probabilities.
And there lies the problem. You have the two most rigorously tested, successful theories in human history using completely incompatible definitions of the exact same concept.
They literally cannot both be true.
That is the crisis. TFH attempts to resolve this massive contradiction by taking a completely different path. It claims that time is not a fundamental dimension of the universe, nor is it an external parameter ticking away on a cosmic clock.
So what is it?
In TFH, time is entirely emergent. It is simply the measure of the wavefront's radial progression through that four-dimensional flat bulk.
So time is literally just the physical movement of this energy wave.
Yeah. Think about it this way. As the wave pushes forward into the 4D space, internal observers like us, who are made out of the complex energy patterns rippling within this wavefront, we experience that forward progression as the flow of time.
Okay, that makes sense.
We build clocks, whether they are pendulum clocks, quartz watches, or atomic clocks, out of the oscillating patterns in the field. Those clocks aren't measuring some invisible temporal dimension.
They are physically measuring how far the wavefront has advanced through the bulk.
Exactly. You don't need a pre-existing time axis for the universe to exist on. The universe doesn't exist in time. The universe is the evolving front.
That shifts the perspective entirely. And this naturally brings us to the arrow of time. This is another massive
A
mystery.
huge one.
Why does time only move in one direction? Why do dropped coffee mugs shatter into 100 pieces, but 100 pieces of ceramic never spontaneously fly up from the floor and assemble into a perfect mug?
Right.
Why do we remember our past, but we don't remember our future?
Standard physics usually blames the arrow of time on thermodynamics and the Big Bang. The idea is that the universe started in a state of incredibly low entropy, meaning high order, and low disorder.
And because of the laws of statistical mechanics, things naturally progress from order to disorder over time.
Exactly, but that has always felt a bit incomplete. It relies on initial conditions rather than a fundamental law forcing time forward.
But TFH physically enforces the arrow of time, right?
Right.
It builds it directly into the wave.
It does, through a mechanism called the universal damping rate, denoted mathematically as alpha zero.
Alpha zero.
According to Bermia's framework, this cosmic wave is not a frictionless system. As the wavefront moves forward through the 4D bulk, it faces resistance. It loses energy. Its overall amplitude decays.
Like friction.
Yes. Because of this universal damping, the progression of the wave is an intrinsically irreversible process. You cannot unring a bell, and you cannot undamp a cosmic wave.
And this is where the theory really starts to flex its unifying power.
If we connect this to the bigger picture of feasibility, the conceptual coherence here is striking. TFH unites three massive phenomena that standard physics has historically treated as completely separate, unrelated mysteries.
Which ones?
The thermodynamic arrow of time, the cosmological expansion of the universe, and the decoherence of quantum states.
Wow. Okay.
In standard physics, these are three different chapters in the textbook. In TFH, they are all driven by that exact same universal damping parameter, alpha zero. The wave propagates, it damps, and because it damps, time only flows one way, the universe visually appears to expand, and quantum superpositions inevitably collapse into single realities.
It's an incredibly elegant unification at the conceptual level.
It really is.
Okay, so the premise holds together conceptually as a beautiful, unified idea. But a beautiful idea isn't enough in physics. It has to actually work.
It has to be feasible.
Exactly.
Yeah.
So let's put it to the test in the classical world. If we are completely throwing out general relativity, if there's no bending fabric of space-time, how on earth do we explain gravity? If space-time isn't real, why does the Earth orbit the sun? Why does an apple fall from a tree?
To answer that, TFH introduces the concept of emergent gravity via topography. The author explains that this moving 3D wavefront isn't a perfectly flat, uniform sheet of energy.
Get some texture to it.
Exactly. It is a finite, configuration-dependent thickness, and that thickness varies depending on what is happening inside the wave.
Let's bring back an analogy here because configuration-dependent thickness can get abstract fast. Let's think about a frozen lake in the dead of winter.
Okay.
The surface of the lake is the boundary between the water and the air, much like our wavefront is a boundary. But that ice isn't uniformly thick. In some places, maybe where the water is calm and freezing cold, the ice is incredibly thick. In other places, maybe near a warm spring or where a current is moving rapidly beneath the surface, the ice is very thin. The ice has a topography to it.
That is a very useful way to visualize it. The theory formally introduces this as the topographic field, labeled T of X.
T of X.
In TFH, what we perceive as matter stars, planets, apples, people, is simply localized, highly structured, dense energy within the scalar field. Because there is so much chaotic, dense energy concentrated in one spot, it alters the local properties of the wavefront. It literally warps the thickness of the front, creating deep valleys in the topographic field.
Okay, so the Earth is a massive swirling knot of energy in this wave. And because it's so dense, it creates a massive valley in the wave's thickness. But how does that explain gravity? If I drop my pen right now, it hits the desk. Why?
It all comes back to that universal damping we talked about, the friction of the wave moving forward. In physics, systems generally want to find the state of lowest energy, the path of least resistance.
Right.
In TFH, the pen, which is just a tiny localized pattern of wave energy itself, naturally moves in a way that minimizes its dissipative cost as the massive wavefront advances.
Meaning the pen wants to take the easiest route forward through time.
Precisely. The area around the Earth is a massive valley in this topographic field because of the dense energy concentrated there. The topography changes the local resistance.
I see.
What we perceive, feel, and measure as the pulling force of gravity is actually just objects drifting down into the topographic valleys to optimize their progression forward. There is no fundamental space-time curving underneath them. There is no invisible graviton particle pulling them.
There is only a scalar wave naturally organizing its internal energy patterns to minimize the resistance of moving forward through the four-dimensional bulk.
Yes. Gravity is just the feeling of falling into a topographical valley of energy.
That is a staggering shift in perspective. But again, being conceptually beautiful isn't enough. To be considered a feasible replacement for general relativity, TFH has to actually do the math.
It does.
Einstein's theory is arguably the most rigorously tested scientific framework in human history. To dethrone it, TFH has to prove it can recover the Newtonian limit. It has to prove that the famous inverse square law of gravity, the math that explains exactly why that apple falls at the exact acceleration we've measured for centuries, naturally emerges from this wave topography. Because if it can't do that, the theory is dead on arrival.
And this is where the Principia documents really shine in terms of mathematical rigor. Bermea dedicates hundreds of pages to deriving this. The papers show that in the weak field, slow motion limit, which is basically the everyday physics of planets and apples, the effective motion of these localized wave packets perfectly mirrors Newtonian mechanics.
So the math max 1-to-1.
It does, but the implications are vastly different. In standard physics, an object's mass, denoted as m, and Newton's gravitational constant g, are treated as fundamental inputs. They are just numbers written into the bedrock of the universe by some cosmic architect.
So not in TFH.
No. In TFH, effective mass and effective Newton's constant are not fundamental. They are emergent responses of the scalar wave. G effective is actually constrained by an equilibrium consistency condition.
What does that mean?
It relates that cosmic damping parameter, alpha 0, to the cosmic mean energy density of the entire universe.
I'm just going to say my mind is genuinely blown by that. Newton's constant, the big G that every physics student memorizes, isn't a constant of nature. It's just a symptom of the wave's equilibrium.
Exactly.
It's a ratio of how much energy the universe has compared to how fast it's losing energy.
It recontextualizes everything, but recovering Newton isn't the ultimate test. General relativity became famous because it solved problems that Newton couldn't. TFH must pass the classic, stringent tests of general relativity. For instance, it has to explain Mercury's perihelion precession.
All right, let's get some context on that. For centuries, astronomers were pulling their hair out because the planet Mercury wasn't orbiting the sun correctly. According to Newton's math, it should trace a perfect ellipse. But its orbit slowly wobbles, shifting slightly over time, a precession.
People were so confused they invented a fake planet called Vulcan.
Right, assuming its gravity was tugging on Mercury. But Einstein proved there was no Vulcan. Mercury is just so close to the sun that the extreme warping of spacetime causes the wobble.
Yes.
If TFH throws out curved spacetime, how does it explain Mercury's wobble?
To pass this test, and others like it, TFH constructs what is called an effective metric. Even though a fundamental fabric of spacetime doesn't exist, internal observers like us, who are forced to use clocks and rulers that are themselves made out of the vibrating scalar field, will measure reality as if it has a curved geometry.
Because our rulers are warping along with the wave's topography.
Exactly. You are measuring a warped system with a warped ruler, so you perceive curved spacetime. TFH defines this effective metric mathematically, using two scalar potentials derived directly from the topographic field, a time potential and a space potential.
Okay.
Bermea demonstrates that in regimes where the topography varies slowly, like in our solar system, the mathematical framework of TFH perfectly aligns with the weak field equations of general relativity.
So it mathematically produces the exact same wobble for Mercury without needing a curved 4D spacetime fabric. What about the other tests? The Shapiro time delay, where light takes slightly longer to travel past a massive object because it has to dip into the gravitational well. Or the bending of starlight around the sun during an eclipse, which famously proved Einstein right in 1919.
TFH handles those as well. The effective metric produced by the topographic valleys forces the trajectory of light to bend and slow down in exactly the way we observe. The author categorizes this current mathematical state of the theory as a level 1 fit.
Let's clarify what that means in theoretical physics, because a fit can mean different things. We aren't just talking about a vague resemblance, right?
No, a level 1 fit means it achieves semi-quantitative mathematical agreement. For local laboratory experiments, binary pulsars out in space, and solar system dynamics, the effective metric produced by TFH solves nearly the exact same geodesic equations and produces the same curvature signatures as Einstein's field equations.
Wow.
So on the classical scale, as a replacement for general relativity, TFH is highly feasible. It preserves everything general relativity gets right about how planets and light move, but it embeds that math in a deeper, physically driven, time-directed mechanism of an advancing wave.
Okay, so this wave topography gives us a beautiful math-backed explanation for why planets orbit stars and why apples fall. But the universe isn't just planets and apples.
Not at all.
If I zoom way, way in past the apple, past the molecules, past the atoms down to the quantum level, things stop behaving smoothly. We enter the realm of quantum field theory, where reality is jittery, probabilistic, and quantized into discrete packets.
Right.
How does a massive, continuous, flowing cosmic wave create discrete, chunky particles? How do we get electrons, quarks, and photons out of a smooth field?
This is where TFH takes its biggest conceptual leap, and it all comes back to the geometry of the wavefront. Standard QFT achieves quantization, this chunkiness, by introducing somewhat abstract mathematical postulates.
Okay.
It imposes canonical commutation relations onto fields. It essentially forces the math to be discrete. TFH argues that discreteness shouldn't be a mathematical assumption, it should be a physical consequence of the environment.
So how does the wave environment force things to be chunky?
TFH relies on geometric confinement. Remember, the bulk of the 4D space is empty. All the energy of the universe is trapped, confined to the narrow, advancing boundary of the wavefront. Because the energy is physically trapped in this narrow band, it can't just take on any arbitrary shape, frequency, or wavelength. It is heavily restricted.
Hold on, let me try to map this to something familiar. If I think about a guitar string is tied down securely at both ends. Because it is physically confined by the length of the guitar neck, when I pluck it, I don't just get a chaotic blur of every sound imaginable.
Exactly.
I get very specific, discrete musical notes. I get the fundamental note, and then I get specific mathematical harmonics above it. The physical boundary of the string forces the vibration to quantize into discrete notes. Are we talking about something similar here?
The guitar string gets us perfectly halfway there. But imagine if, instead of a physical string made of nylon or steel, the string is just a boundary of pure energy trapped between the empty 4D space ahead of it and the empty 4D space behind it.
Okay.
Because the scalar field is geometrically confined within the physical thickness of the wavefront, it sets up what physicists call Bessel-type eigenmodes.
Okay. Bessel-type eigenmodes is a terrifying phrase. Let's translate that. Are we basically just talking about the specific allowed vibrating patterns of this trapped energy, like the 3D equivalent of the natural harmonics on that guitar string?
That is exactly the right translation. An eigenmode is just a natural pattern of vibration for a specific geometry. Just like a drumhead has certain ways it can naturally bounce up and down, the confined energy in the wavefront has specific, discrete ways it can vibrate.
I see.
These allowed vibrations manifest in our reality as discrete particles. Quantization in TFH doesn't arise from abstract mathematical rules. Discreteness emerges naturally from the physical boundary conditions of the advancing wave.
That is incredibly elegant. It grounds quantum mechanics in physical geometry rather than just pure math.
And this leads to one of the most striking, rigorous predictions in the entire hypothesis. By calculating the lowest non-trivial confined mode of this field, basically, the lowest possible note this cosmic guitar string can play, TFH predicts a fundamental scalar mass gap of exactly 2.05 giga-electron volts, or GeV.
2.05 GeV. That is a highly specific number. And in theoretical physics, a parameter-free prediction like that is the holy grail, isn't it?
It absolutely is.
It means you didn't just tweak the math until it gave you the answer you wanted. The geometry of the theory demanded that specific number.
It is a massive claim. This 2.05 GeV fundamental particle theoretically anchors the entire excitation spectrum of the TFH universe. According to Bermea, all other known particles, the quarks, the bosons, the electrons, their masses and properties theoretically scale up as higher harmonics or complex resonances of this fundamental geometric vibration.
Okay, so we have a physical mechanism for creating particles. But quantum mechanics isn't just a list of particles, it is a whole framework of weird behaviors. TFH has to reproduce quantum mechanics itself. Specifically, it has to explain the Schrödinger equation, which is the famous mathematical formula that dictates how quantum probabilities evolve over time as waves of chance.
TFH tackles this head-on. The Principia demonstrates that if you look at the slowly varying envelopes of these localized high-frequency wave excitations, meaning if you zoom out just a little bit from the ultra-fast vibrations of the particles, their effective dynamics naturally obey a mathematical structure that looks exactly like the Schrödinger equation.
Really?
Yes. In the narrowband weakly damped limit, the mathematics of the moving wavefront smoothly reduces to the deterministic unitary evolution we are familiar with in standard quantum mechanics. The probabilities evolve exactly as standard physics says they should,
Okay.
but there is a massive catch, and it is a feature, not a bug. Because TFH has that universal damping parameter alpha 0 driving the entire system forward, the perfect unitary evolution of the Schrödinger equation is only an approximation. It doesn't last forever.
Here's where it gets really interesting. We're about to connect the macro to the micro.
Exactly. Over time, that cosmic damping, the friction of the wave, causes what the author calls a universal decoherence floor. The exact same mechanism that drives the macroscopic expansion of the universe and forces the arrow of time to only move forward inevitably acts on the quantum level to cause quantum states to collapse.
Meaning quantum superpositions can't last indefinitely.
hmm
We've all heard the thought experiment of Schrödinger's cat, right? The idea that a cat in a box is simultaneously both alive and dead in a superposition of states until someone opens the box to look at it and the wave function collapses into a single reality.
A classic.
Standard quantum mechanics struggles to explain why or how that collapse actually happens physically. But in TFH, the universe literally drags the superposition into a single state through damping friction.
The theory provides concrete numbers for this, which makes it highly testable. The decoherence timescale is tied directly to the Hubble scale, which relates to the expansion rate of the universe.
So what are the numbers?
For the universe as a whole, that timescale is roughly 14 billion years. But when you scale the math down for mesoscopic or macroscopic laboratory systems, like trying to keep a large molecule or a computer chip in a quantum superposition, the universal damping dictates an absolute physical limit on how long that superposition can survive. No matter how perfectly you isolate it in a vacuum or chill it down to absolute zero, the wave of the universe will eventually force it to collapse.
That is a phenomenal bridge between quantum mechanics and cosmology. But as we evaluate feasibility, we have to be objective. Where does this fall short? Because you mentioned earlier that replacing QFT is the most ambitious part of this.
And it is where the theory is currently the most vulnerable. This raised a huge flag for feasibility. To his credit, the author is very transparent about this in the Principia's refinement needed logs.
Oh, good.
While TFH can derive a Schrödinger-like equation and propose a highly compelling physical mechanism for decoherence, it is currently lacking a full mathematical derivation of the non-abelian gauge groups.
Okay, non-abelian gauge groups. Let's translate that for the listeners. What does that actually mean for the feasibility of the theory?
It means TFH has not yet mathematically proven how the strong and weak nuclear forces emerge from the wave topography. We know the strong force holds the nuclei of atoms together, and the weak force is responsible for radioactive decay. Standard QFT models these flawlessly using incredibly complex math involving non-abelian gauge groups. TFH hasn't replicated that math yet. Furthermore, it doesn't have the exact spin statistics mathematically mapped out for fermions, like electrons, versus bosons, like photons.
So it explains that particles are vibrating wave modes, but it hasn't mapped out the complete dictionary of how all those specific vibrations interact to create the nuclear forces we see.
Correct. The author explicitly logs this as a level 0 conceptual fit for the full standard model of particle physics. A level 0 fit means the underlying mechanism is conceptually consistent and the geometric logic holds up. But there is massive, rigorous, highly complex mathematical work left to do before TFH can truly claim to have replaced quantum field theory. As of right now, it is the weakest link in the current feasibility of the entire hypothesis.
So if we take stock classical gravity is looking very strong with a level 1 mathematical fit, quantum mechanics is looking incredibly elegant conceptually, offering physical reasons for things like wave collapse, but is mathematically incomplete at level 0. Now, let's step out of the solar system and the quantum lab and look at the whole universe. Let's move to the cosmological crucible.
The big picture.
This is where TFH really tries to flex its muscles by tackling the darkest, most agonizing mysteries in modern astrophysics, dark matter and dark energy.
These are the ultimate proving grounds for any new theory. Because if you look at the standard model of cosmology, the lambda-CDM model, it paints a very unsettling picture of reality. It basically states that everything we can see, touch, and interact with, every star, every galaxy, every dust cloud, makes up roughly 5% of the universe. The other 95% is made of stuff we can't see, can't interact with, and don't understand.
It says the universe is roughly 68% dark energy and 27% dark matter. And despite decades of searching, we have no idea what either of those actually are. Let's start with dark energy. Why do we even think it exists?
We know it exists because in the late 1990s, astronomers measuring distant supernovas discovered something shocking. The universe isn't just expanding, that expansion is accelerating. Galaxies are flying apart faster and faster. To explain this acceleration, standard cosmology posited a mysterious, invisible, anti-gravitational force pushing the universe apart. They called it dark energy, and standard physics models it mathematically using a cosmological constant, denoted by the Greek letter lambda.
But isn't there a massive problem with how quantum field theory tries to calculate dark energy? I've heard it called the vacuum catastrophe.
It is famously considered the worst theoretical prediction in the history of physics. When physicists use the equations of QFT to calculate how much energy should exist in the empty vacuum of space, due to virtual particles popping in and out of existence, the number the math spits out is 120 orders of magnitude larger than the dark energy we actually observe accelerating the universe.
120 orders of magnitude. If an accountant was off by 120 zeros on a tax return, they wouldn't just be fired, they'd be studied by scientists as an anomaly of nature.
Exactly.
But in theoretical physics, it's just a Tuesday. They just slap the cosmological constant lambda into the equations as a fudge factor to make the macro math match the telescopes, completely ignoring the massive failure of the quantum math.
It's a pragmatic patch, but it's physically unsatisfying. TFH, however, says dark energy isn't a mysterious new substance filling the vacuum. It isn't a magical anti-gravity fluid, and it certainly isn't a cosmological constant. Dark energy is simply the optical macroscopic effect of, you guessed it, our old friend, the universal damping parameter, alpha zero.
Everything comes back to the friction of the wave. How does damping cause the universe to look like it's accelerating apart?
Think about the mechanics of a wave. As the scalar wave propagates through the 4D bulk, its overall amplitude decays because of damping. As the amplitude drops, the physical wavelengths of the excitations confined to the front naturally elongate. They stretch out. Now imagine you are an internal observer, a human being, living your whole life inside that stretching wave. When you look out at a distant galaxy, the light reaching you has been stretched along with the wave. You interpret this wavelength stretching, this physical elongation, as an expanding universe.
And because the dynamics of the wave change as it loses energy, it visually appears to an internal observer as an accelerated expansion rate at late times.
Precisely.
So there is no mysterious fluid pushing galaxies apart. It's just the visual effect of the universe losing energy to friction as it moves forward through the fourth dimension. That is a massive paradigm shift.
And the math supports it beautifully. The TFH master equation literally forces the damping parameter, alpha zero, to perfectly mirror the Hubble parameter, h0, which is the number we use to measure the expansion of the universe. It ties the expansion directly to the thermodynamic arrow of time.
Okay, so dark energy is solved by wave damping. But what about dark matter? Because that's a completely different problem.
Yeah.
Dark energy pushes things apart, but dark matter pulls things together. When astronomers look at galaxies, they spin way too fast.
Yes, they do.
Based on the laws of gravity, if you count up all the glowing stars and the visible gas in a galaxy, there simply isn't enough mass, enough gravitational pull to hold the galaxy together at the speeds it's spinning. It should tear itself apart and fling stars out into the void. Standard physics says the only explanation is that galaxies must be surrounded by massive, invisible halos of undiscovered ghost particles, dark matter.
And physicists have spent decades building massive underground detectors looking for these WIMPs weakly interacting massive particles or axions. And despite billions of dollars in incredible engineering, we haven't found a single direct trace of a dark matter particle.
So what is the TFH alternative? If there are no invisible ghost particles, what is holding the galaxies together?
TFH proposes a radical alternative called enhanced warping. Let's go back to the topographic field we discussed earlier, the ice on the lake. TFH states that the topography of the wave holds a physical memory of past scalar fields stirring. In the chaotic, highly turbulent early days of the universe, right after the Big Bang, the wave was incredibly violent. That massive turbulence carved incredibly deep, lingering ridges and valleys into the topography of the wavefront.
Almost like massive cosmic scars left behind on the wave itself.
Exactly like scars. This warped topography, which the theory denotes mathematically as rho warp, persists in the geometry of the wave even if the luminous visible energy that originally caused it, Rovis, has moved on, dispersed, or settled down.
So when an astronomer looks through a telescope at a galaxy and sees it spinning too fast. They aren't seeing the gravitational pull of billions of invisible particles.
No, they are seeing regular, visible stars and gas falling into massive ancient valleys in the topography that were carved out billions of years ago by early cosmic turbulence. The extra gravity is just extra steepness in the topographical valley. Dark matter phenomena are entirely separate from luminous matter. They are a geometric memory of the past, born from the same underlying scalar field dynamics. You don't need a new particle, you just need to understand the history of the wave's shape.
If I'm a listener right now, I might be thinking, this is incredibly cool science fiction, but why should I care? How does this impact the real world of astronomy today? Well, right now, astrophysics is facing what they call the Hubble tension. It is arguably the biggest crisis in modern astronomy, and it threatens to break our entire understanding of cosmology.
The Hubble tension is a profound problem. Essentially, we have two different ways to measure how fast the universe is expanding. If we look at the extremely distant ancient universe, specifically the cosmic microwave background, which is the afterglow of the Big Bang, we can calculate an expansion rate. Let's call that the early universe number.
But if we measure the expansion rate by looking at relatively nearby supernovas and pulsating stars in our current local universe, the late universe number, we get a completely different result.
And as our telescopes have gotten better, like the James Webb Space Telescope, the measurements have gotten so precise that we know for a fact the error isn't in the instruments. The two measurements fundamentally disagree. The early universe says it should be expanding at one speed, and the late universe is expanding noticeably faster. Standard physics is at a complete loss to explain why.
If we connect this to the bigger picture, this tension is where TFH might offer an incredible lifeline to the astrophysics community. The crucial question is, can one single choice of TFH parameters fit both the early universe and the late universe data perfectly?
TFH provides a framework where the Hubble tension isn't an actual physical contradiction at all. Bermea suggests the tension is entirely an artifact of fitting a damped wave universe into the wrong mathematical model. The mainstream community is using the standard lambda CDM model, which assumes a static cosmological constant, to analyze the data. If you use a static mathematical ruler to measure a universe that is actually an inherently dissipative, decaying wave, your early and late measurements are naturally going to clash because the wave's properties are changing over time as it damps. TFH promises that if we analyze the data using the mathematics of a damped scalar wave, the tension dissolves. The early and late universe align perfectly under the umbrella of universal damping.
This brings us perfectly to the final phase of our deep dive, the ultimate test falsifiability and future-proofing. In science, a theory is only as good as its ability to be proven wrong. You mentioned string theory earlier. A major criticism of string theory is that whenever an experiment doesn't match the math, theorists can often just tweak a parameter or imagine another hidden dimension to hide the mathematical flaw. It's incredibly hard to falsify.
The author, Bermea, makes a bold claim right in the text regarding exactly this. He states that a new paradigm is only as strong as its risk of failure. TFH is not like string theory. It is tightly, purposefully overconstrained. It is highly vulnerable to observation, because everything stems from a single scalar field and a single damping parameter. Alpha zero, if one piece fails, the whole theory dies. If the calculated alpha zero parameter doesn't match the quantum decoherence rate and the macroscopic Hubble expansion rate simultaneously and perfectly, the theory's dead. There are no extra dimensions to hide in.
That vulnerability is the hallmark of good, honest science. And to that end, the Principia outlines a concrete test menu of highly specific, falsifiable predictions. These are specific observations where TFH expects to see reality deviate from the predictions of standard general relativity and quantum mechanics. If we build the instruments and look, we will either see standard physics or we will see TFH.
The test menu is rigorous. The first major prediction is universal accelerations. Because the entirety of the wavefront is constantly relaxing toward equilibrium as it advances, TFH predicts that everything in the universe is experiencing an incredibly weak universal background acceleration of roughly 10 to the negative 18 meters per second squared.
That is an unimaginably tiny number.
It is a...
The second test involves what Bermea calls topographic lensing. As we discussed, standard models assume dark matter is at least loosely tied to the history of normal visible matter. Where there is normal matter, dark matter generally clusters. But TFH predicts that because the wave topography retains ancient scars, there should be a population of over-lensing systems out in the cosmos.
Yes, these would be regions of space where the gravitational lensing, the bending of light systematically, vastly exceeds what standard cold dark matter models can explain. Regions where the topography was warped incredibly heavily in the chaotic past, without ever requiring massive amounts of luminous matter to be there in the first place. If we find these stark, isolated gravitational anomalies that completely break the dark matter models, TFH offers an immediate explanation.
The third test involves damped gravitational waves.
Hmm.
A few years ago, LIGO made history by detecting gravitational waves for the first time, the ripples in spacetime caused by merging black holes. If gravity in TFH is just a ripple in the topography of this advancing wave, then those ripples must be subject to the same cosmic damping friction, alpha zero.
Exactly. Standard general relativity predicts how those waves should travel through an empty vacuum. TFH predicts that when we measure what are called standard sirens, like merging black holes or neutron stars, at massive gigaparsec distances across the universe, the gravitational waves arriving at Earth will show specific cumulative damping signatures, a slight loss of amplitude and stretching that general relativity insists should not be there.
And finally, the redshift drift. TFH predicts highly specific mathematical corrections at low redshifts compared to standard models. Upcoming precision sky surveys using new observatories coming online in the late 2020s could actually measure this drift over a period of years and definitively prove whether the standard model or the TFH wave model maps reality closer. But for the mainstream academic physics community to truly take this seriously, TFH has to finish its homework. We talked about it being a level 1 fit. It has to move to a level 2 precision fit.
The author is clear-eyed about what that road to level 2 looks like. Theorists working on TFH must derive explicit post-Newtonian 1pn derivations.
Let's unpack 1pn. What is a post-Newtonian derivation?
It's essentially the next layer of extreme mathematical precision beyond basic gravity. It accounts for all the tiny relativistic corrections required to perfectly match the highest degree of modern solar system tests. It's the math needed to navigate a satellite precisely past Jupiter. TFH needs to publish those exact rigorous derivations. Furthermore, they need massive, supercomputer-driven 3D fluid dynamic simulations of the wave topography. They need to computationally prove that the scars left in the wave actually form structures that look exactly like the dark matter halos we observe around galaxies today.
And the final piece of homework for level 2.
The most critical piece. They need to write a TFH-specific version of cosmological code. Currently, cosmologists use complex software like CMB to simulate the universe based on standard physics. TFH theorists need to build a simulation that precisely maps the acoustic peaks of the cosmic microwave background using only the parameters of a damped scalar wave, proving once and for all that their model natively resolves the Hubble tension in full simulation.
It is a massive multi-year undertaking for a whole team of physicists, but the blueprint is explicitly laid out in the texts. So if you step back and look at the whole board, what this hypothesis is really asking us to do is profoundly beautiful. The time force hypothesis takes the most complex, agonizing, contradictory puzzles of modern physics. The invisible ghosts of dark matter, the vacuum catastrophe of dark energy, the relentless one-way arrow of time, the bizarre collapse of quantum superpositions, and the fundamental geometric nature of gravity itself, and attempts to solve them all with one single dissipative four-dimensional wave. It is a pure energy-only ontology.
It bravely attempts to strip away the magical invisible fabrics, the extra hidden dimensions, and the ghostly dark particles that standard physics has relied on for decades. It replaces them with fluid-like dynamics, physical topography, and geometric resonance. And while it is vital to remember that it currently lacks the rigorous mathematical completion of the standard model's quantum sector, its feasibility as a unifying classical framework is remarkably robust. Its vulnerability, its overconstrained nature, and its falsifiable predictions ensure that it will be rigorously tested, proven, or destroyed in the coming decades.
As you move through your day today, as you experience the forward march of time ticking on your watch, as you feel the gravity holding your feet firmly to the floor, think about what this hypothesis is suggesting. You aren't moving through an invisible bending grid of empty space. You are quite literally a complex pattern of energy riding the crest of a four-dimensional cosmic wave, constantly decaying, constantly pushing forward against the friction of existence.
And this raises one final important question to mull over. A provocative thought building directly on the implications of Bermia's source material. We've established that if TFH is correct, our entire observable universe, everything we have ever known, seen, or touched, is merely the thin, three-dimensional boundary of this advancing scalar wave. So what lies in the four-dimensional bulk space that the wave has already passed through?
Wow.
If time is just the progression of the front moving forward, does the wake of the wave still exist behind us? When the energy front moves on, what remains? Is the entire history of the universe, our literal past, every moment that has ever happened, physically etched as a stagnant, low-energy geometric memory into a deeper, currently inaccessible dimension of that vast energy ocean?
Now that is something to unpack. We are just ripples on the crest, leaving a wake in the fourth dimension. Thank you for joining us on this deep dive.